As you can see, these questions are posted on YouTube channel already. Okay, the answer is also there. So when you are free, you can practice. Moreover, I'm going to solve only the average difficulties problems, and I will also post them on YouTube channel. The easy one I will not solve because there is around 20 or 21 questions. Okay, the easy one you can solve it yourself. So let's wait. You can start solving, but I will start solving from problem number 3, 6, 8, 9, 10, and so on. Okay. So I think we can start now solving from problem number 3. Okay. Yes.
We define flux as V, yes?
Flux? No. F. B is a magnetic field, so it still didn't come to that point. Have you answered the question? Okay. What is here? So basically, we have large charged. Okay, what we have? Okay. So we have a large charged sheet, and we have a square-shaped area of the sides are given. So we have basically large charged sheet. Let's say it's like this one. Okay. Let's say it's positively charged. Now, it's very large. So when it's positively charged, you will expect that it will have electric field lines, right? So it will have electric field lines on both sides, okay? Not only one. How many sides it has? Two sides, right? So we have this side, which is area, make it this one, and the other side, okay? Which is E, and call it just A, okay? Now they brought the square plate. What is it? Square shaped area of the side 5 centimeters. So let's just call it D, okay? And it found that the flux from there is given, okay? So what do we have to find? Flux is given, the sides is given. What is the electric flux through the sheet? Okay, this is a flux is given. Find the charge density on the sheet. Charge density, area charge density, okay? Sigma. So how can we find it? We have first flux formula, right? Flux is equal electric field times area, right? And since we have two sides of this charged large sheet, you have to write it as a E times 2A, okay? Because this is large charged sheet, okay? It has two areas, not only one. And we also brought some square-shaped things, and flux is given. And this is also equal to what? Q enclosed, or total charge on this large sheet, divided by epsilon naught. Correct? Now, the formula of the area charge density is equal to what? Total charge divided by area. Correct? Okay. So flux is given. Now from here, wait a minute. So we have okay. If that's the case, then we can somehow work with this formula and to bring it as a E times 2 times epsilon naught is equal Q divided by area, correct? If we take this formula, and this Q over A gives you sigma, correct? So you have this formula. So the sigma final will be equal to E times 2 times epsilon naught. And also the area itself is equal to the D squared, correct? Now, do we know the E? No, how can we find E then? Using this formula, correct? So that means we can say that flux is equal E times D squared. This is area, correct? And from here, E will be equal flux divided by D squared. And we bring it here, this equation again, we say that flux over D squared times 2 times epsilon naught. That will give you area charge density. Okay. Next question. Next question will be problem number 6. Read it, try to understand the question. Have you answered the question? Okay. Have you taken all the values? At least take the important message, okay? Write down all the values because you have to tell me while I'm solving. Okay, so what we have no, before we have silver, aluminum, right? We have aluminum sphere, correct? Now it's metallic. When you put the charge on metallic sphere, what will happen? Oh, the charges will repel each other and they will go far away from each other. And when it will stay only reside on the surface of the metallic sphere. Okay, so when you charge it, all charges will go outside. That means if you want to find electric field inside those metallic sphere, what will be the electric field inside? 0, because no charge. No charge, no electric field. Okay. When it comes to insulator, it's different story. In insulator, charges will be equally distributed throughout the volume. Okay. But in metallic, all the charge will go outside and it will reside only on the surface of the metallic sphere. Now, the Q is given, correct? Amount of charge. And the radius is also given, right? What we have to find? We have to find electric field at the distance of this R. Okay. This is a 5. This is 10. Correct. So what you have to do is basically you have to draw Gaussian surface. Okay. It's imaginary surface just to find electric flux, to make it easy your life. Okay. To finding the flux, so electric field and so on. Now, if that's the case, then we have to find electric field at this distance. Okay. When R is equal to 10. So what is the formula? E is equal K Q divided R squared. Okay. Any questions? Now you have to put the values and you can find the answer. Okay, next question. Next question will be 8. Have you answered the question? Okay. At least you taken notes, right? The given values. Okay. So we have a charged rod. Okay. Have 10 charged rod. Is it positively charged or negatively charged? Negatively charged. Okay. What else is given? It's not a charge. It's a linear charge density, lambda. So lambda is equal to what? Negative 7 minus 6 column divided by centimeter, right? Lambda itself is equal to Q over L. The L is this length of the rod. Okay. What else is given? So long silver rod of the radius 3 centimeter. So the radius is given. Find the electric field. Mhm. So the radius of the rod is given, right? So this is small r. So let's call it this r, which is 3 centimeter, correct? You have to find electric field at a distance of 5 centimeter. Okay, so what we have to do? You have to first draw imaginary Gaussian surface. Okay, at the distance when r is equal to 5 centimeter, correct? So let's say that this is r is equal 5 centimeter. Okay, suppose. So what you have to do is you have to draw area of the Gaussian surface. So how it's going to be? It's going to be like this one, correct? And then this is all Gaussian surface, okay? Imaginary, okay? So you have to find electric field at the distance r is equal to 5. Now electric field will be pointing inwards, right? Now, if you look at here, electric field is everywhere along this road, okay? Not only that point. So we have electric field everywhere, okay? Along this road, right? Now, a flux is equal EA, correct? Which is also equal to Q enclosed inside this rod divided by epsilon naught, right? We also know that the lambda is equal Q over L. Now, how can you find the area of this Gaussian surface when r is equal to 5 centimeter? How can you find it? What is equal to in formula?
Area of the cylinder.
Area of the cylinder, yes. Area of the cylinder.
PR over R. Oh, wait, not over R.
So you take this Gaussian surface, okay? You cut it. You fold it. What you will get? You will get triangle, right? Not triangle, sorry, the rectangle, right? So this is L, suppose. What will be this upper side? 2 pi r, correct? If you cut this Gaussian surface, you fold it out, you fold it, and you will get this L. Okay, let me make it big L, okay, because this is big L. L times 2 pi r, right? If that's the case, then the area of this rectangle will be 2 pi r times L. Yes? So we'll bring it here. We say that electric field is equal, area is equal 2 pi r L, right? Which is also equal to Q divided by epsilon naught. What is next? How can we get lambda, linear charge density? What do we have to do? Q over L, right? Correct? So we can make it like E times 2 pi r is equal epsilon naught, we can bring it here, Q divided by L. So that gives you lambda, correct? So that means finally we can say that lambda is given, correct? Small r is given, epsilon is given. We have to find electric field at distance of small r, which is 5 centimeters. That means finally we can say that R is equal lambda divided what? Epsilon naught 2 pi R. That's it. So this is a formula, okay? So lambda is given. Sorry, yeah, should be E, guys. E at the distance of R. So lambda divide epsilon naught 2 pi R. That's the final formula. Any question? Okay. To better understand the previous question, we have to solve problem number 7. Did you get the answer? Okay, so what we have charged sheet, right? What is given? Charge density is given, correct? Sigma, which is equal Q over A, right? This is given. What else is given? Epsilon naught is given, okay. What do we have to find? Electric field just above this surface, right? So as I said already, it has two sides, the sheet, right? This A and this A, right? As side. That means flux is equal E times 2A, okay? Correct? It has two sides. We are finding flux not only from one side, flux, total flux, which is from both sides, okay? Is equal Q enclosed divided by epsilon naught, right? That means E is equal Q over 2 epsilon 0 A, correct? And Q times A gives you sigma, right? Which is area charge density, which means sigma divided 2 epsilon naught. Okay. Okay, if it's clear, then what is next? Problem number 9. Yeah, let's look at the 9. This is similar also to the previous question. 9. Okay, tell me. So what we have there? We have, is it metallic? Okay, so we have a ball, right? What is the radius? Radius is given, correct? And then what else is given? Electric field is given. R is given, correct? And we also have this distance is given, correct? Okay. What else? That's all. The electric field toward the center of this, all right? So that means, first of all, we have to draw a Gaussian surface on the sphere, correct? And we know that electric field is pointing towards the center of the sphere. That means it has negative charge, right? Okay. Electric field is given. Okay. So we have Gaussian surface, which is the area of this sphere, right? Imaginary sphere of the Gaussian surface. So flux is equal, E times A is equal Q over epsilon naught, right? What is the area of this Gaussian surface here? 4 pi r squared, right? But in this case is what? R is equal to what? R plus D squared, because we're looking for this total R, okay? Correct? It's very important. You have to count it from the center of the object. And is equal Q over epsilon naught. Oh no, sorry. So that means I can say that E times 4 pi R plus D squared is equal Q over epsilon naught. So that means Q is equal E epsilon naught 4 pi R plus D squared. Correct? Is that okay? And what is given here? It's a question 9, right? Okay. So when you do calculation, obviously you have to know exactly yourself, okay, when you put in the values that this is negative charge, okay? Because electric field pointing towards this spherical ball. So therefore, when you're writing answers, should be negative something column, okay? Okay, now let's look at the chapter 7. From chapter 7, let's start from the bottom and we'll go up, okay? Hmm? Good question. What is the value of epsilon naught? No. It's the constant 8.85 epsilon naught. 8.85 times 10 to the power of minus 12. Okay. Okay. So problem number. Let me look at what we have here. So let's start. Okay. I think we can just even start from the first question. So the first question is very simple, right? We have Q1, we have Q2. What do you have to find? We have D. We have to find electric potential energy, right? Not just electric potential. Electric potential is V. Electric potential energy is U. The unit is joule. So the U is equal K Q1 Q2 divided by D. That's it. So D is given, Q1 Q2 is given. Okay. Next question. Okay, in the second problem, what we have? We have proton, right? Then the electron was brought far away, right? To a distance of d. Okay, from far away to a distance d. You have to find how much work was done, correct? So the formula of the work is equal to the negative of potential energy, correct? And your potential energy is equal K Q1 Q2 divided by D, correct? So that means you have negative K is equal 9 times 10 to the power of 9. The charge of electron 1 is a positive proton, which is positive 1.6 times 10 to the power of minus 19, multiplied to the negative of electron, negative charge, correct? Electron 1.6 times 10 to the power of minus 19, divided by D, okay? Now, since you have negative with another negative, your final answer will be positive something joule, okay? Very important, guys, when you're finding, you have to know the sign, okay? Problem number 3. In this problem, you have two parallel plates. Okay. Now the distance between them is given. An electric field is also given. Let's say this is positive, this is negative. This is the direction of your electric field. You have to find potential difference. Very simple, right? V is equal E times D. Okay. Problem number 4. The 4 is easy, so let's look at the problem number 5. Have you understood the question? So we have parallel plates. Okay, so let's just look at from the one side, okay? The distance between them is 10 centimeter, right? This is equal to 0. This one we don't know, but at 8 centimeter, this V is equal, let's say, I don't know, what is the value? 64 volts, right? You have to find electric field. The electric field here is the same, constant, okay? Same value, all of them are equal, okay? Whatever point you take. So how can you calculate it? So E is equal V over D, but this V should be delta V, correct? Delta V, that means is equal so you have 464 volts minus 0 volts, okay? Divided by what? 8 centimeters. 10 to the power minus 2 meters, okay? Next question will be problem number 8. Let's look at the 8. You have to find energy in kilo electron volt, right? To accelerate the electron. So what is given? E is given, D is given. You have to find U in kilo electron volt, right? 1 electron volt is equal to what? 1.6 times 10 to the power of minus 19 joules, right? So if you want to find U in kilo electron volt, then what you have to do is, in general formula will be QED, right? Now, since you want to find in kilo electron volts, you have to divide it by 1.6 times 10 to the power of minus 19 and times 3, right? Because it should be in kilo. Is correct? Okay. So that means this Q itself is equal 1.6 10 to the power of minus 19, right? So we can cancel this one with this Q. You will end up with ED divided times 10 to the power of 3. Okay, and that will give you energy or in kilo electron volt. Correct? Okay, so that's it.